Hi, I welcome you all to this session where we are going to see about the various types of motions bodies undergo, the various types of oscillations, and how these motions and oscillations are represented as waves. And taking you along on this journey is Dr. Yunus Jerusha, an assistant professor of physics. We would have seen various types of oscillations and waves around us. But based on scientific principles, let us get to know what is an oscillation and what is a wave. An oscillation is a to and fro motion of a particle about its equilibrium position. It is the repetitive variation, usually in time, of some measure about a central value, frequently a point of equilibrium or between two or more different states. A wave, on the other hand, is produced by a disturbance. It propagates energy and momentum from one place to another without the transport of matter. Waves consist of oscillations or vibrations of a physical medium around relatively fixed locations. In the picture of this ripple diagram, it is observed that the waves originate from the center of the ripple and progressively move outward. Natural oscillations of a physical system are caused by the properties of the system itself as a result of the disruption of the state of equilibrium. It is observed so in the case of a person who is running. Waves, we know, propagate in a medium. Therefore, the medium should have various properties in order to support wave propagation. Let us see what those properties are. Elasticity is one of the properties. It is required for the particles to return to their mean position after disturbance. Secondly, inertia is required for the particles to store energy and overshoot their mean position. Thirdly, friction. This among the particles of the medium must be minimum. Otherwise, the propagation of the wave is going to be disturbed. And last of all, the medium itself. This medium should have uniform density for the wave to propagate in a smooth manner. Now, for some characteristics which a wave must possess in order for it to propagate. 1. It requires a medium for its propagation. 2. A wave is basically a disturbance caused in the medium. 3. The wave travels through the medium. 4. During the wave propagation, the medium particles vibrate simple harmonically about their mean position. 5. A phase difference is produced amongst the successive particles of the medium. 6. The particle velocity during their vibration varies with position. 7. The wave velocity in a particular medium is constant and it depends only on the nature of the medium. And last of all, the energy also is propagated along with the wave motion without any net transport of the medium. Of the various types of motion present, the most common type of motion is the periodic motion. A periodic motion is any motion that repeats continuously on a definite path in a definite interval of time, and this interval of time is called as the time period. The path of the periodic motion may be linear, circular, elliptical, or any other curve. There are two types of periodic motion, the first one being the translational motion. Here, the motion of the body moves linearly with time. Second, we have the rotational or the oscillatory motion, where the motion of the body repeats itself after a regular interval of time. We just saw that periodic motion consists of two types of motion, the translational and the rotational or oscillatory motion. Let us look at some examples for the translation motion. One is the running of a train on the railway track. Secondly, we have the launching of a rocket. And for the case of the rotational or oscillatory motion, we have the simple pendulum, the beating of a heart, and the motion of the earth around the sun. There is another type of motion called as the simple harmonic motion. We say that a body or an object or a particle undergoes simple harmonic motion when the acceleration of the particle or the object is proportional to its displacement and is always directed towards the mean position. There are two types of simple harmonic motion. One, the linear simple harmonic motion, where the displacement of the particle executing the simple harmonic motion is linear. Secondly, there is the angular simple harmonic motion, where the displacement of the particle executing simple harmonic motion is angular. Some examples of objects which undergo linear simple harmonic motion are the motion of a simple pendulum and the motion of a point mass suspended with a spring. Some examples for the angular simple harmonic motion are the oscillations of a compound pendulum and torsional oscillations. Some of the conditions for executing simple harmonic motion are: the potential energy must be minimum at the position of stable equilibrium. There should be no dissipation of energy, and the acceleration A must be proportional to the displacement y and opposite in direction. As per the definition of a simple harmonic motion, the acceleration of the particle must be proportional to the displacement and should always be directed towards the mean position. If F is the force which is applied to a body in order for it to undergo a simple harmonic motion, and thereby let's say that the object undergoes a displacement y, then the acceleration undergone by that object is given by d square y by dt square, which is equal to the negative of the displacement. Here we see that the acceleration is directly proportional to the displacement y, and this equation here therefore is the equation for a simple harmonic motion. It is a second order differential equation in y, where omega is the angular velocity and is given by omega is equal to square root of k by m, where k stands for the force constant or the spring constant having a load m attached to it. Some of the features of a simple harmonic motion are: it should be the periodic motion of the particle. The particle must oscillate back and forth about its mean position with a constant amplitude and fixed frequency, and the restoring force acting on the particle must be proportional to the displacement from the mean position, and the force acting on the particle must always oppose the increase in the displacement. There are 6 characteristics which characterize a motion to be simple harmonic. Let us look at each of them now. First is the displacement. It is the particle's distance from the mean position at that instant. It is given by y is equal to a sine omega t, where a stands for the amplitude and omega stands for the angular velocity. Y is given here in the diagram. This is small y, the displacement which the spring undergoes during its oscillatory motion. Next is the amplitude. It is denoted by capital A and it is the particle's maximum displacement covered by the body on either side of the mean position. The maximum amplitude is given here in the diagram. Next characteristic is the time period denoted by capital T, which is the time taken by the particle to complete one vibration. T is given by 2 pi by omega, where 2 pi stands for the total angular displacement and T in terms of the acceleration is given by T is equal to 2 pi square root of displacement by acceleration. T in the diagram is given here. It is measured as the time period from one crest to the adjacent crest or from a trough to the adjacent trough. The next characteristic on our list is frequency f. It is the number of vibrations or oscillations made by the body in 1 second. It is given by the reciprocal of the time period or the ratio between omega, the angular velocity, and the angular displacement 2 pi. The next characteristic is angular velocity omega. It is given by 2 pi by t, or in terms of the acceleration, it is the square root of the acceleration to the displacement. In terms of the force constant, omega is given by square root of k by m, where k stands for the force constant. And last of all, we have the phase, which is the physical quantity that expresses the instantaneous position and direction of motion of an oscillating system. Oscillations are of various kinds, and based on the force acting on the system, we have 6 different types of oscillations. They are the free oscillation, forced oscillation, damped oscillation, resonance oscillation, coupled oscillation, and maintained oscillation. Of these 6, we will be concentrating on the free, forced and damped oscillations in detail in the forthcoming videos. The first ideal oscillation is the free oscillation. If a system oscillates freely without any resistance like friction, such oscillations are known as free oscillations. This is practically not possible because there are always some resistances which are offered to the oscillatory motion. Next come the forced oscillations. When a body oscillates under the influence of an external periodic force, its oscillations are not with its own natural frequency but with the frequency of the external periodic force. This type of oscillation is said to be a forced oscillation. In the picture shown here, we have a boy swinging and his friends are pushing him forward. Some more examples are a tuning fork set into vibration due to external force, a floor vibrating due to the marching of soldiers and the bob of a simple pendulum held in the hand and then given a number of swings by the hand. The next type of oscillation is the damped oscillation. When the amplitude of the oscillations of a body decreases gradually with the passage of time due to friction, we call such oscillations to be damped oscillations. Damping basically is a reduction of amplitude of vibration or oscillation due to external forces like friction, air resistance, or other resistive forces. The amplitude and energy of the system also decreases. Some examples are, first, as shown in the picture here, when a mass is suspended in a spring and is set into vibration in air, it will take a long time to come to rest. But if the same mass is set into vibration in a bowl containing water or oil, the frequency of oscillation and the amplitude of oscillation decreases quite rapidly. Another example which can be quoted is a pendulum which is displaced from its equilibrium position oscillates with a decreasing amplitude and finally comes to rest. The next type of oscillation is the resonant oscillation. These are oscillations in which the frequency of the driving force is equal to the natural frequency of the oscillator itself. Therefore, there is a matching of the amplitudes of oscillation, and as a result, the total amplitude is very large. Some examples are shown here. The first animation shown here is the breaking of a wine glass by sound. Also, there are cases where glass window panes are shattered by a passing aircraft. In labs, tuning forks can be set into vibration by the vibration of another tuning fork. The next type of oscillation is the coupled oscillation. It is basically a system of two or more oscillators linked together so that there is a mutual exchange of energy between them. And such types of oscillations are called as coupled oscillations. The best example for coupled oscillations occurs when two simple pendulums are coupled by a spring. The last type of oscillation is the maintained oscillation. Here, energy is continuously supplied from the outside at the same rate at which the energy is lost by it. Therefore, the amplitude of oscillations is maintained to be a constant. An example is shown in the animation. The amplitude of the swing will not reduce if someone on the swing is pushed continuously in a periodic manner. To recollect quickly, we've seen what is meant by a wave, motion, and oscillation. We've also seen the various types of motion and the various types of oscillations too. In the next video, we'll be seeing in detail about the various types of oscillations, the equations involved, and their solutions. Thank you so much for your patient listening.